Hello, welcome to the first installment of Teacher V's AP Stats probability question of the day. Today we are going to start things off from 2015, question number 3. We are given the probability distribution of this variable x, the number of ATMs working on a day at the mall. Sometimes there's no ATMs 15% of the time. When there's only one open, that's 21% of the time, and so on. So we're given the variable x takes on 4 different values, and then below it is the probability that x equals any of these numbers. So this is the probability x equals 0, the probability x equals 1. And our first question is, what is the probability that at least one ATM is working when the mall opens? At least one means we want the probability that x is greater than or equal to 1, at least 1. So there's a couple different ways to think about this. That means we can either add up these 3 right here, or that would be the same thing as just taking 1 minus the probability that x equals 0, which is what I'm going to do for fun. So the probability that at least one ATM is working is the opposite of the probability that no ATMs are working. So this would be 0.85. Part B, what is the expected value? So that means when I go to the mall, on average, how many ATMs are going to be working? And it's usually not going to be a whole number, because this is like on average for a great number of days, what would be the average number of ATMs working. So it's pretty much like a weighted average. So we're going to take each of these values and multiply by their probability. That's what the expected value is we're going to take all of the x values and multiply by their probabilities and then add it up. So we want 0 times 0.15, 1 times 0.21, 2 times 0.4, and 3 times 0.24. And that all adds up to 1.73 machines. Here's an important note, is that we need units. Units are important in AP Stats. So we're talking about the number of ATMs working. So we really want to include this units. So I'll put that on the side as a highlight. Units are important. What is the probability that all 3 ATMs are working when the mall opens, given that at least one is working? So when we see this word given, this is a conditional probability. We want the probability of A given B. So if we review that for a second, the probability of A given B is the probability that both things happen divided by the conditional, the condition that B happened. So let's translate this sentence into mathematical probability notation here. We want the probability that all 3 ATMs are working would be the probability that x equals 3, given that at least one is working, which is what we just did up top. X is greater than 1. So now let's unwind this conditional definition. So we want the probability that x is 3 and x is greater than 1 over the probability that x is greater than 1. But if x equals 3 and x is greater than 1, that's just x equals 3. So we have the probability that x equals 3 over the probability that x is greater than or equal to 1, which is 0.24 divided by what we previously found to be 0.85. So we're taking the probability that x equals 3 and dividing by the probability that x is greater than or equal to 1. And that gives us 0.24 over 0.85, which is approximately 282. So that's part C, the conditional question. And let's see what D is asking us, probably the hardest part. Given that at least one ATM is working when the mall opens, what would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected from B? So I'm not a great reader here. So if we have the condition that one is open, how many ATMs do we expect to be open? So there's no more, zero is never going to happen anymore. So we expect this to go up. And what I want to do is I want to really dig into this more than just what they're asking and define a new variable y to be the number of ATMs open given that there's at least one open. So I'm going to say the number of ATMs given, which is the important word, that x equals or is greater than or equal to 1. So let's create this probability distribution, just like they did up here. They list the different values the variable can take on and the probabilities associated to each of those values. So let's do that for this new variable y. It's pretty much the number of ATMs given that there's already one open. So y can take on the values. There can be one ATM open, two ATMs open, or three ATMs open. And now what's going to be the probability of each case, the probability that the big variable y takes on one of these values, 1, 2, or 3. Well, we already found 3. That's what we did up here. The probability that x equals 3 given that x is greater than 1. And what really happened there was we took the probability that x equals 3 and divided by the probability that x is greater than or equal to 1. So we can do that down here for 1 and for 2. We already have 3, which is 0.282. And if we need to do 1 and 2, I'll do a little scratch work below. We're going to take the probability that x equals 1 and divide by the probability that x is greater than or equal to 1, and same thing for 2. The probability that x equals 2 and divide by the probability that x is greater than or equal to 1. And I did this earlier, is 247 and 0.471. So that's the probability distribution for y. Now let's find the expected for y. So we're going to take that weighted average of this new table over here. We're going to take 1 times 0.247 plus 2 times 0.471 and 3 times 0.282, which means we're going to take 1 times the probability that x equals 1 and 2 times, I don't know why I did so many parentheses here. And that all adds up to be 2.04 machines. So the very long answer to this question is that the expected value definitely goes up. And we have just quantified that new expected value. Before it was 0.173, but now we've just cut out the option that it could be 0 at all. We're taking all of these and then just dividing by 0.85 is that conditional distribution. So I hope you learned something. Have a good